In this session, we'd like to apply the Laplace transform to another differential equations, heat equations. Heat equation is expressed round u round t equal k times the second partial derivative of u with respect to x. Boundary condition at the x equals 0, u equals 0. So temperature u is 0. At the x equals 1, u is fixed to the constant temperature of the u sub 0. As the initial condition, u becomes 0. We Laplace transform of the heat equation. This heat equation, so Laplace transform of the both sides of the equation. Then for the derivative of the u with respect to t, it becomes a s times the Laplace transform of the capital U minus the initial condition. So initial condition is included here, equal k times the second derivative of the Laplace transform of the capital U with respect to x. This is 0. So it becomes a second order ordinary differential equation. So this equation quite easy to solve. So solutions of this ordinary differential equation is expressed c sub 1 hyperbolic cosine square root s over k times x plus c sub 2 hyperbolic sine square root s over kx. This is a solution. Then we need to determine the coefficient of the c sub 1 and c sub 2 using the boundary condition. So we need to Laplace transform of the boundary condition of the u at x equals 0 and the u at x equals 1. This expresses the capital U at x equals 0 and the capital U at x equals 1. This is equal to the 0 because the initial condition, this is 0. So Laplace transform of the 0 becomes 0. And then u at x equals 1, this is the constant value of u sub 0. So constant value of the u sub 0, Laplace transform to becomes the u sub 0 over s. This is Laplace transform. Then using the two equations, we need to determine c sub 1 and c sub 2. You substitute x equals 0 into these equations. Then hyperbolic cosine 0 is 1. So this is c sub 1. Hyperbolic sine 0 is 0. So c sub 1 equals 0. For the second equation, u at x equals 1 s becomes c sub 1 has already become 0. So c sub 2 hyperbolic sine square root s over k equal u sub 0 over s. You can determine the c sub 2 using these equations. So we determine c sub 1 and c sub 2 by substitute back into the original equations. We could find the capital U. This is the capital U is u sub 0 hyperbolic sine square root s over kx over s times hyperbolic sine square root s over k. You can use an exponential function to describe hyperbolic sine. So this equation becomes u sub 0 over s exponential square root s over kx minus exponential minus square root s over kx over 2. This is a hyperbolic sine. And this is exponential square root s over k minus exponential minus square root s over k over 2. And the 2 is going to be cancelled off. Then if you divide it by the exponential square root s over k in the numerator and the denominators, it becomes these equations. Then if you look at this, it's exactly equal to this one. If you consider the 1 plus alpha square plus alpha cube plus blah 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 up to the infinities, this is equal to the 1 over 1 minus alpha when alpha is less than 1. So we know that these relations, in this case alpha corresponds to these quantities. So it's expressed with sigma. So this is expressed sigma I equals 0 to the infinities alpha to the I. So this corresponds to the alpha to the I. Then we change the 1 over 1 minus exponential minus 2 times square root s over k. Then it's split into the two terms. So we have discovered the equation for the Laplace transform of the capital U. Then to find out the solutions of the heat equations of the temperature of the U, we need to inverse Laplace transforms. Then we exchange the term of the sigma and the inverse Laplace transforms. When we study the Laplace transform, we derive the Laplace transform of the complementary error functions of the a over 2 square root t is equal to the exponential minus a square root s over s. Then we are going to use this equation. This corresponds to the a. So it becomes inverse Laplace transform of the first terms correspond to this one using the complementary error functions. And the second terms, this corresponds to the a. So it is expressed the complementary error functions. This is a solution expressed with the error functions. Or you can express the solution with the complementary error functions. Then I'd like to show you the numerical result. When the u sub 0 is 1 and the k is 1 and we take into the 100 terms, so it's impossible to consider the infinite terms, so 100 terms. Then at the t equals 0, so this is the initial condition of the u sub 0, 1, and this is 0. And the heat is transferred from the x equal 1 to the x equal to the 0. So temperature is increasing. At the t equals 0.02 and at the t equals 0.2, almost straight lines. So we could solve the heat equations using the Laplace transforms. Also, we could use a method we learned when we studied how to solve the non-homogeneous boundary value problems. So I'd like to show you how to solve the heat equations. To solve these equations, actually we consider two functions. U is composed of the two functions of the v is the xt plus psi as only the function of x. Original heat equation is divided into the two equations. First equation, k psi prime equals 0. As a boundary conditions, psi 0 is 0. Psi 1 equal u sub 0. For the second equation for the v, so round v round t equal k second derivative of v with respect to x. For the boundary conditions, v0t equals 0, v1t equals 0. For the initial condition, vx0 is a minus cx. So we change the original equation into the two different equations. So first equation is the ordinary differential equation. It's quite easy to solve. Psi x becomes the c sub 1x plus c sub. So because the second derivative becomes 0, so we can easily integrate twice to become the c sub 1x plus c sub 2. So from the psi 0 is c sub 2 is 0 from the boundary conditions. And the psi 1 is c sub 1 equal u sub 0. So we obtain the psi x, the u sub 0 x. This is the psi x. Once we determine the psi as a function of x, we are ready to solve the second equations. Round v round t equal k second derivative, and the v0t equal v1t equals 0. This is the boundary condition. As the initial condition, vx0, it becomes minus u sub 0 x. This is the initial condition. So by solving the heat equations with the boundary conditions, vxt is expressed and start from the 1 to the infinities. A sub n exponential minus kn squares pi square t times sine n pi x. So using the boundary conditions, we could solve the heat equation. This is the general solutions. Then we'd like to determine the a sub n using the initial condition. So a sub n is determined to integral 0 to the 1 b x0 sine n pi x dx. Then you can substitute vx0 is a minus u sub 0x. So this becomes minus 2u sub 0, 0 to the 1, x sine n pi x dx. You can use the integration by part. Then it becomes 2u sub 0 over n pi minus 1 to the n. You can substitute back to the this a sub n into the here. You can find the v. And the original u is obtained sum of the v and psi. So solution of the u xt is given by sigma n equal 1 to the infinities 2u sub 0 n pi minus 1 to the n exponential minus k n squares pi square t sine n pi x plus u sub 0 x. Because of the psi, this is the psi x. This is v xt. Actually, the x, you can use the Fourier series expansions. X is expressed n equal 1 to the infinities 2 over n pi minus 1 to the n plus 1 sine n pi x. So you can substitute this into the here. Then u xt is expressed u sub 0 sigma n equal 1 to the infinities 2 over n pi minus 1 to the n exponential minus k n squares pi square t minus 1 sine n pi x. So this is another solution form to describe the temperature of u. Then we'd like to compare the two solutions. So I show the if you use a separation of variable method, this is a solution. So this solution is expressed by the blue ones. And the orange color is a solution given by the error functions. So two solution is very similar, but if we just only take into the small number of the terms, 10 terms, given by this method, is a little bit difficult to show the solutions. It's oscillating solutions. But if we increase the number of terms, we consider two solutions approach very well. So from these simulations, we find out we need more terms to have a convergent solutions if we use a separation of variable method compared with the solutions expressed with the error functions. Okay, this is the end of this session.